his bachelor's degree from Tsinghua University. His research interest lies in the interdisciplinary regions among quantum foundations, quantum algorithms, machine learning, and statistical physics. And recently, he focused on constructing and explaining the quantum speedups from the perspective of dynamic evolution. So let's welcome Yizhou.
Okay, thank you for your introduction and thank you for your invitation. And today I will talk about our present work, recent work about quantum speedup for non-convex optimization via quantum tunneling works. And this is the archive paper. And this work is a joint work with Professor Wei Jiesu and Tongyang Li. You can ask any question during this talk. It's fine. And first, let us introduce non-convex optimization. Optimization problem is a very fundamental mathematical problem. Like we are given a function, normally a high-dimensional function, and we want to find the minimum point or optima of this function. And for non-convex optimization, which is typical landscape is shown like this figure. We have many local minima, saddle points, and the goal is to find the global minimum. So this fundamental mathematical problem have many applications, important applications, especially in the machine learning problem, like training a machine learning model is often understood through optimizing a loss function. So a lot of research on understanding neural networks will ultimately transform to understand how we optimize a loss function. How is the optimizer? How is the landscape? By landscape, I mean the loss function, actually, because we know the loss function, if you add a constant, any constant on loss function, it would not change its structure. So we just call it as landscape, which, refer to the function. Okay, so in terms, so our research actually focuses on the optimizer or the optimization method here. For classical methods for optimization, we will go to details later. They have access only to the local information about the function, and they make use of that the local information to update and to find minimum. And the most widely used or well-established classical method is stochastic gradient descent. Actually, for the simpler version, gradient descent, its intuition is quite clear. We just take demand the local information, which is the gradient of the point, and we go to the direction, which is negative gradient direction. So you will decrease, and that's for convex functions. We have guarantee that the gradient descent will converge, but for non-convex, it's highly likely that you will go to a local minimum, not a global minimum. So people have this kind of stochastic gradient descent, which means in practice, when you take the when you are asking the gradient or calculating the gradient, you will sample several points, right, in a small ball, which we call a mini batch. And if you sample enough, many points, you will get the exact gradient or get a better approximation. But if you choose few points to approximate the gradient, actually you won't get the actual gradient, but like some kind of vector have a deviation from the actual gradient, and that kind of deviation can be modeled as a stochastic thing. So here we can model the stochastic gradient descent as like we have original at the kth step at xk, and we have a actual gradient, right? And since we do not have the actual gradient, the vector we have is actual gradient plus a stochastic term, and the step size is s. So we're updating our points into xk plus 1 by this rule. Here we often model this stochastic term as a Gaussian. As Gaussian, or in the continuous time limit, which means s is very small, it will become like a Brown motion. And from the physical perspective, you can understand this as some kind of thermal motion. And it can be shown that this learning rate s will like serve as some kind of temperature, or as some kind of temperature, like it will demonstrate how strong the thermal motion is. So for this kind of classical algorithms, there are, like as I mentioned, some fundamental difficulties. Mainly is because they have only local queries to the only have access to local information of the landscape. The like rigorous define of what is local queries or local information is given as follows. It's like we determine the kth step by the k minus 1 and all previous steps or previous points. And how to like determine the next step, we use previous steps function value and arbitrary order of derivatives, right? And all this information, function value or derivatives of points, they are local. So you are just using like this local information of previous points to determine next step, which point you will arrive. And this kind of algorithm is called like algorithm based on local queries. And almost most like classical algorithms can be put into such formulation. And intuitively, this kind of algorithm will have some fundamental difficulties when facing locally non-informative landscape, right? By locally non-informative, we are talking about like if you only use function value and the derivatives, you cannot infer the global trend of this function. There are some examples like vanishing gradient, like this graph, right? At a very large region, you have no gradient, so the function values also are the same. And by local queries, you cannot know where the local minima probably be. And another kind is like non-smoothness. For example, this graph, if you only take local information, like local value and local derivatives, you cannot know the global trend of this function. And sometimes we know recently there are some like rigorous results on manifold. So the manifold, if a manifold have some kind of negative curvature, the curvature will like hide some kind of global trend of the function. If you are like running optimization on the manifold, and you only have local information. The local information cannot like tell far away because the manifold itself has some structure, and it can distract your it can distract the optimizer. So facing these fundamental difficulties, we're also thinking about other possibilities. And since quantum, actually, we see that quantum evolution or quantum algorithms provide us such a new possibility, because like I'll mention here that they are actually not satisfying this local queries definition. But when constructing quantum algorithms, actually you can arbitrarily construct an algorithm, right? What's the direction for us to construct one with speed up? Actually, the key is that we want some kind of speed up, otherwise we don't need quantum algorithms. And here, we use the perspective of dynamic evolution. Like when we understand the classical algorithms, we think it as some kind of non-equilibrium thermodynamics, right? Thermal process. So that's the intuition why they can go to minimum or overcome the saddle points, the barriers. And we're just thinking if there are unique like quantum dynamics that can help us overcome barriers and find other minima. And there is one, right, which is quantum tunneling. This is actually this actually has a long history, right? People have this intuition that quantum tunneling can help us escape from local minima. And this kind of dynamics or mechanism is non-classical, right? It's totally quantum, it's unique, so we expect it to have some kind of quantum advantage on this kind of problem. And another point, which is true for all kinds of like quantum evolution, although on a quantum computer, when you simulate it, yeah, you think of like a circuit model, right? The qubits, you only like use local gates between qubits, but actually you are in the state space. You think the state, it evolves in the state space, which is not local in the position representation of the system we are simulating. So yeah, although the qubit, we use local gates between qubits. In the states, the state also evolve globally. So actually, if you say in the position representation of the system we are simulating, it's not local in position. And the key for us, we are just simulating the Schrodinger equation. And this is some kind of preliminary things I should tell you here. We are simulating the Schrodinger equation in this form. Here we set h bar equals to 1, and h bar over 2m, h bar square over 2m as h square. Yeah, so it's you can think we can tune the mass m to this h parameter, and we will call this h parameter as quantum learning rate, similar to its classical learning rate. We will see the similarity between these two tunable variables or parameters. And for quantum tunneling, yeah, I will like use a toy model to talk about like quantum tunneling briefly. So if we consider this double well situation, first think that phi 0 and phi 1 is phi 0 is the ground state, of this Hamiltonian, right? If you set fx as this double well case, and phi 1 is the first excited state of this Hamiltonian. And they can be represented by a kind of superposition, which is phi plus and phi minus. We will call here the phi plus and phi minus as local ground states. Like the superposition of local ground states will form global ground states and global first excited states here. Actually, there are some more mathematical definitions regarding this local ground state, and I will briefly talk about what do I mean by local ground state. So first, you can think about a situation like we cut off this well, and in the feasible region, right, in the X, which is in our one-dimensional case, you just cut off this region, and you will have a new landscape, and this boundary of this well will serve as some kind of boundary of this new function, and at this boundary, all functions will all wave functions need to be zero. And for such a landscape, for such a Hamiltonian, you will have a ground state, which is definitely localized here because you have cut off this region. And similarly, for this well, you can cut off the left one, and you will have a local ground state. When the quantum learning rate h is small enough, this original local ground state will form or approximately form the low energy subspace, which contains phi 0 and phi 1. So we just make a projection from this original local ground state to the low energy subspace and do orthogonalization, and we'll find this phi plus and phi minus, which is more rigorously called orthogonal local ground states. Later, when we talk about local ground states, we are talking about orthogonal local ground states. And these local ground states have the property that first, they are local, right? They are local in one well. And second, their superposition can form global eigenstates. So although it's difficult to think the following situation that a particle can overcome a well that's an energy well which is higher than its own energy, but in quantum mechanics we think it as some kind of based on linear algebra, and it's quite clear. It goes through a Schrodinger equation evolution, right? If we started from phi 0, if we started from phi plus, phi minus, here is phi minus. If we started from phi minus, and the wave function will be written as this. So since they have the global eigenstates, they have different energy, their rotation velocity, this E0 and E1, the phase, right? Their rotation velocity is different. So they will have a phase difference. And when this phase difference is -1, and you will get the phi plus state. So it's just in a linear space, and from one state rotate to another state, and you will have this transformation from a local state to another local state. The key is that this local state actually span the subspace, the low-energy subspace of this Hamiltonian, and the Schrödinger equation actually evolve with respect to this eigenstates. And physically, it's like this tunneling, right? You have a tunnel because you don't have the energy to go to the mountain, to go to the top. The probability of finding the particle on the mountain or on the top is always small, but you like mysteriously the probability from at here decrease and at here like goes up. It's easier to consider like just in a linear space. And knowing this dynamics, actually, we want to construct some kind of algorithm or use this dynamics to explain quantum speed up. And here we like sort out like two questions, major questions for us. The first one is on what kind of landscapes can we design algorithms by quantum tunneling? This question actually is not that trivial, because if you want to have a clear picture of quantum tunneling, you need to have some restrictions, which I'll mention. And the second question on the landscapes, right, satisfying the demand by the answer of question one, like we specify on what kind of landscape the quantum tunneling can actually be faster or give rise to quantum speed up. It can beat classical algorithms, like the representative one, SGD, right? So in answer these two questions, in trying to answer these two questions, we have our own like philosophy or methodology. The first is that we study the algorithms from the perspective of dynamics, classical or quantum. We focus on their dynamics. For classical ones, it's like thermodynamic, non-equilibrium thermostochastic process. And for quantum ones, it's just quantum dynamics. And like in terms of mathematics, right, we focus on the continuous time limit. It's like we perform this quantum evolution in quantum computers, and it's just quantum simulation. In quantum simulation, you must like discretize the time, right? You're like performing different gates. So in actual cases, the time is discretized. And for classical, like SGD, the time is also discretized. You see S is the step size, how you like update your points step by step. So the time is also discretized. But here we focus on the dynamics, the continuous time limit. And for SGD, it will become SDE, which is a stochastic differential equation. And for quantum, yeah, just the Schrödinger equation. And for quantum tunneling, it's a little bit tricky. Actually, quantum tunneling is, people have this intuition for a long time that quantum tunneling may help. But previously, most studies focus on quantum annealing. In many quantum annealing research paper that they claim that they have some kind of speed up because of quantum tunneling, but they cannot clearly state when quantum tunneling appear. Right, the picture of quantum tunneling in annealing problems is not that clear. So to establish such a clearest picture, we will have some restrictions or simplifications. So it might not be the most practical case, but it is the case that show the dynamics, quantum tunneling dynamics most. and which will serve as some kind of building blocks for us to understand like more complicated settings. And I will mention in the end of this talk how our framework will like help to explain or understand quantum annealing, yeah, which is more like practical. So for answering the first question, we will have, as we said, we have some simplification. Like our main problem is focused on such landscapes whose local minima are approximately global minima. And starting from one local minima, we want to find all other local minima or to hit certain target minima. And from a pessimistic like perspective, we need to do this because if you want to have a clear picture of quantum tunneling, and if you are just evolving a simple like Schrodinger equation, you know, Schrodinger equation is like it satisfies energy conservation. So if you want to have tunneling between local minima and you want to satisfy the energy conservation, the two local minima or the two local ground states, they need to have the same or approximately the same energy, right? So this demand like ask the local minima also need to have approximately close function values. Actually, this may be like loose. I will mention that also later. And from a like optimistic perspective, that this problem is still important because it's crucial for generalization property. Like it's also a long intuition for us that flatter minima have better generalization properties. So although you can find like one minima of landscape of the loss function, you probably need to find more and sort out the one with best generalization property. And this is also important for sampling, right? You want to like sample different local points or local minima. And here we introduce like also in answering question one, like we are constructing our algorithms. So on the landscapes, like satisfying our main problem, the one we showed in our main problem, we have this QTW or quantum tunneling works that initiates actually it's just at the ground, it's a Hamiltonian simulation or quantum simulation problem. We start this simulation of Schrodinger equation or the Hamiltonian from a local ground state. This actually can be generalized as long as you start in the low energy subspace. That's okay. You always stay in the low energy subspace and you will like explore all the minima. But for local ground state, it's more likely to be prepared. That's because if you find one local minima, you can put some state there, right? And that's close to that. Yeah, is pretty close to local ground state if h is small. And you start from such a local ground state and measure the position at a time t, which is chosen uniform from this interval. Yeah, I will, yeah, talk into the details of this. This is inspired, or this is the same as the quantum walks. And to solve the main problem asks us to explore all minima or hit one target minima, right? So that actually is just we need to explore just study the mixing time and the heating time. And actually, these two times both satisfy this following expression, right? We can take tau as this. So poly n is just a polynomial of n. And this n is the number of local minimum or global minimum. And delta E is the minimum spectrum gap of the Hamiltonian in the low energy subspace. Actually, it's the energy of first excited state minus the energy of ground state. And for small h, we have the following expression. And I will also explain this in the next slide. So for theorem 1, actually to understand this, we can like map a continuous landscape to a graph. Like take this figure as an example. You have this local minimum or wells, right? Every minimum or well can be mapped to a vertex. And if two wells have some kind of quantum tunneling effect, yeah, there will be an edge between them. And these edges like have different strength. It is imaginable that some wells are closer, so the tunneling effect is stronger, right? So this is a weighted map, but undirected. And starting from local ground state is like you start from one vertex and measure the position at a time from uniformly chosen from this interval. This operation is to make sure that we will have a converged distribution, because we know if you just evolve the Schrodinger equation, it will explore all the points like repeatedly, right? It's just always walking between the points. It will never converge. The wave function will never converge. But if you apply such a method, just like quantum walk, the distribution you got will converge to some fixed number. And like in the quantum walk problem, the key is the spectrum gap or energy gap of the Hamiltonian or of the graph Laplacian, right? Here is the same, but actually our primary focus is on this Hamiltonian H. H is an operator in infinite dimensional space. But since we are in a low energy subspace, right, we restricted ourselves. We're starting from local ground state, so it's nearly in a low energy subspace. We can express the H restricted in the low energy subspace as a matrix. And if you choose to expand this matrix in the basis of local ground states or local ground states, you will have such a matrix. And the diagonal elements are just energy of this local ground states. And the off-diagonal elements is just the tunneling strength or tunneling amplitude between wells. Like if it's ith row and jth column, it is the tunneling strength between the ith and jth wells. So this matrix, we call it as interaction matrix, is similar to the graph Laplacian in quantum walk. And so the mixing and heating time will be written as this. This, yeah, which is, yeah, the same as the quantum walk. But one thing is different is the delta E. Here, the delta E actually is determined by this tunneling strength, because when you calculate the energies of the local ground states are almost the same. So the difference of eigenstates is just determined by this off-diagonal terms. And these off-diagonal terms are estimated in like operator studies with some techniques as WKB approximation, and we can have such delta E. This S0 is called the Eigenmann distance between two wells. It's just an integral from here to here, and I will show the form of this later in the next slide. And H is just the quantum learning rate. The key thing, we need to like remember or understand is that this S0 not only depends on the height of the barrier, but also the distance between wells, because it's an integral from here to here. Okay, so this is just an application of using theorem 1, like what problem we can solve. We find this tensor decomposition problem that will satisfy our assumption on the landscape, and there will be evolution time or total time we needed for finding all the minima here. So in answering question 2, like on in what cases we will have quantum speed up, we first compare like our quantum algorithm with stochastic gradient descent. So for stochastic gradient descent, if you read it as SDE and do some further mathematical exploration, you'll find its convergence time is also an inverse spectrum gap. This inverse spectrum gap, this spectrum is called Witten-Laplacian. And this spectrum gap can be given by this formula. And the key takeaway is that this spectrum gap, the exponential term here, depends only on the height of the barrier. And S here is the classical learning rate. So take the left down picture as an example. The S0 here is an integral from x1 to x2. Actually, the square function value dx is such an integral. And the HF, the barrier height here, is just like the height of this. So it's imaginable that for thin but high barriers, the quantum ones, S0 will like remain small, but the classical one will be much larger. And when we compare quantum algorithm with classical algorithm, we compare them following the protocol that we keep their accuracy the same and compare the running time. The accuracy is like at last how close we will find, how close to the local points will hit, right? And this accuracy will be determined by H and S. So actually H and S here are connected by accuracy. If we do not like have some kind of restriction on H or H and S, you cannot compare these two algorithms because they have free parameters, right? You keep the accuracy the same, so H and S will have some kind of restriction, and then compare the running time. And it's just like comparing S0 and HF, something like this. And the first thing is what will like change the running time or the comparison. The first thing is about integral property, which is actually the width and sharpness, or actually it's just this S0. This will determine the exponential terms here. If it's thin and tall, yeah, quantum will definitely beat classical one. And the second is zero order properties, like the distribution of wells. You can take our QTW like simply as quantum walks. This distribution of wells will change the graph structure, and this graph structure will determine the polynomial term here. So if it's more symmetric, the polynomial will be smaller, right? And the third one is about the differential property, or the flatness of this minima. We find that for flatter minima, quantum algorithm is more is easier to reach high accuracy. So at that case, H can be larger, and the running time will be smaller compared to the classical one, because for flatter minima, S will be smaller, need to be smaller to reach the same accuracy. And these are our mean information or mean messages from the comparison between QTW and SGD. Also, our next step is we want to construct some kind of large quantum classical separation on certain cases. And the case we are constructing here is consists of 2 wells and 1 bridge. First, this problem is classically hard. Why? You think this large B is a high-dimensional ball, and this SV is the slab region. This is a high-dimensional ball, and this slab region have some width in the direction V. V is a special direction which pointing to another well. And in the 2-dimensional case, you see this SV is actually very small. But on high-dimensional cases, this SV region will occupy most area, most measure, or rigorously speaking, most measure of this ball. So if you are initially in this well minus, which means actually you are mostly likely in this SV, it's hard to get out, because if you only have local information, and in this SV, local information cannot provide you any information about V, because inside SV, the function is isotropic. So actually, if you make queries in SV, it cannot provide you any information about V, and your next step is irrelevant to V. And since it's just you are randomly picking points in SV, because they're irrelevant to V. And if you want to get out this SV region, you need the queries, which is the measure, the ratio between measure of SV 1 minus SV over the whole region. So we can prove that this number is exponential in the dimension. So it's a hard problem for classical optimizers initiate in W minus and to go to W plus. But for quantum algorithm, we see that if we have well design of this W minus, BV, and W plus, and we have the local ground state of W minus, we will be able to use a tunneling to heat W plus in like with queries sub-exponential in D or like polynomial in D. That's some kind of separation. But actually, we also find this paradox that quantum algorithm, if we only use the queries to the function, we are not able to like hit the W plus region with polynomial queries, because we can do a reduction from Groover search, like how the whole BV and W plus region is inside such a cap, is inside this high dimensional cap, and we can have like exponential. When I say exponential, I mean exponential in the dimension D. We can have exponentially many caps inside this ball, right? Disjoint caps inside this ball, and we can map each cap to a point in the Groover search problem, and we can use the Groover search oracle to construct such a continuous landscape. And if we can solve this problem polynomial in D, which means we can solve the Groover search with like, if you have, actually in the Groover search problem, there will be points exponentially in D. And the Groover lower bound is square the number of points. So it must still be exponential in D. And our results will violate the Groover lower bound, right? Which is not possible. So actually, it's because our algorithm can do this because we give its local ground state. And if we go back to say a simple example, we will see that this local ground state is not isotropic, right? The local ground state like tell you something about this spatial direction itself. And here comes a question which we haven't solved, but very interesting is that whether we can have some kind of real separation, which means like in our algorithm, even we given this initial state, our quantum algorithm can make use of this local ground state. It only needs like constant number of copies, yeah, to do the evolution and hit. But for classical algorithms, even we give them the distribution of this local ground state, it might still be hard for classical algorithms to like sample it or make use of this distribution to hit W minus W plus. So it's still an open question if there will be some kind of real separation if we do not, if we give classical algorithms the access to this local ground state. And later we did some numerical experiments. Actually, due to the difficulty that classical computers cannot simulate quantum systems, we just did like low dimensional experiments on the quantum simulation cases. And to verify or to illustrate our theorem 1, which talks about the theorem 2 actually, which talks about the comparison between SGD and quantum simulation. We do like we compare them on such one-dimensional cases. You say example 1, this landscape have almost the same like barrier height with example 2 case, and example 1 have the same flatness with the example 3, but have different like barrier height. And we find that actually the barrier height will have more influence or have large effects affecting the heating time. So you will see that if we change the flatness, it seems that quantum heating time is still similar to classical ones, but if we change the barrier height, the separation is very clear. Also, we use we can simulate high dimensional classical cases. So we verify the classical hardness of the constructed problem, which is the theorem 2, which is the landscape in theorem 2, the W minus W plus case with SGD. It can be shown that there is a lower bound envelope that for different learning rates, and it's always like the query grow exponentially with respect to the dimension D. And at last, we test the relation between convergence time and the quantum learning rate on this two-dimensional case. And you can see that the theoretical bound and the experiment result agrees well. Actually, our contributions can be organized into 2 points with the perspective of understanding algorithms from dynamics, right? First, we give an algorithm or an algorithm framework of QTW, and then we give an example of possible quantum speedup. In understanding our results, from mathematics, you can understand the comparison between QTW and SGD from comparing Witten Laplacian and Schrodinger operator, which is the Hamiltonian. And from physics, actually, you are comparing thermal climbing dynamics and quantum tunneling dynamics. And from algorithm, you are comparing local queries or local evolution between the quantum global evolution. And here are actually many important open questions. First is that our assumptions about the landscape is actually quite many or quite restricted. And if there are possibility to lose our assumptions, there definitely are, and we're trying but there will involve more discussions on the quantum learning rate H, because essentially we just want the energy between local ground states to be similar or to be the same. But in this work, we demand H to be small enough. So the energy, which actually is related to H, if you still want local ground state to have the same energy, your local minimum, the potential energy must be also similar, because H stands for some kind of kinetic energy, right? If kinetic energy is small, you want the potential energy to be close in order to make the total energy similar. And another direction is that except quantum tunneling, if there are the unique quantum dynamics that can help us to have better optimization performance. Actually, we are recently thinking about quantum spontaneous emission, which is a unique quantum thing, right? And yes, some kind of quantum dissipation systems. Yeah. And the third question, actually, as I mentioned, is how can we understand annealing or quantum tunneling in annealing based on our findings? So we here have a intuitive or straightforward quantum annealing strategy, that we change the quantum learning rate. You actually physically you tune the the kinetic energy, right? You slowly make the kinetic energy being slow. And similar to like in relativity, we have instantaneous rest frame. Here we may introduce like this instantaneous local ground states. And through this kind of instantaneous local ground states, you can see tunneling, the picture of tunneling clearly. And at last, yeah, as we mentioned, if we can, in the previous slide, if we can find some kind of real quantum classical separation in terms of the copies of initial state we give, yeah. And our work actually received a lot of help from other professors and our students, which we are very grateful. And thank you very, very much for inviting me to give this talk. Yeah, thank you. See if you have any questions. Yeah, and this reference.
Thank you. Is there any question from the audience?
Hi.
Yeah.
I was wondering, so like for this algorithm, we need to, like say if I want to using it on arbitrary cost function, so I just substitute the f of x in the Schrödinger equation. And so then, but I need to like calculate the ground state first and all the ground states.
You do not need to calculate the ground state. Like we need to calculate or estimate local ground states in order to analyze it. Yeah, like if you are running this, you just like prepare a local ground state in one local minimum, in one well, or and that's fine. And you can initiate it. Yeah.
So then I have to somehow know how much local wells, local minimas they have.
We need to know it in our analyze, but if you are running it, you also don't need to know. You only need to know one minimum, and you can use that minimum to start. And other minimum, the algorithm will find them for you. Yeah.
Okay. Oh, so it's like so maybe I'm doing some optimization, and so I got some minima. I don't know whether it's global or local, but I can further use this algorithm to see whether it can give me some other minima. Is it like
Yeah. From the version of this work it is, but like if we can like some kind of annealing algorithm, we change this h, right? We can explore like different minima, like of different energy, and that will be more powerful. Yeah, there is actually a very strong restriction from the results of mathematics that we can analyze high dimensional cases when h is very small, or actually is the semi-classical analysis. Yeah, in mathematics it's called semi-classical analysis of Schrödinger operator. It demands this h to be small so that we will have the spectrum gap. But when h is large, the approximation or estimation will be like difficult.
Okay,
but we can have some empirical tests. Yeah, when h is large.
Thank you.
Thank you.
So can I think of this as a kind of Hamiltonian simulation? I mean, you need to know potential. This is the function you want to find the minimum, and you put into the Hamiltonian, and you start from some local minimum, and they evolve to see how quickly it can reach another minimum.
Right.
And
but yeah, please.
And so you mentioned that tunneling cannot give you converge, but somehow you manipulate a converge. What's the reason that you can make it converge?
Oh, right. Yeah, it's if you know like quantum walk, yeah, it's just like I can explain it from from another perspective. Okay, it's like you consider it in a subspace. If you are randomly choosing a measuring time, like from an interval, you will automatically prepare a mixing state. Like if you just measure the state in a fixed time, you will get the distribution of the pure state. But if you are randomly choosing the measuring time, actually equivalently, you prepared a mixing state. And if you calculate this mixing state, you will find like the mixing state is just a matrix, right? The density matrix. You will find its off-diagonal terms will decrease, will converge to zero, but the how to say, the diagonal terms will remain constant, which means this state, this mixing state you are preparing will converge. So that, and if you calculate its observables, like the position, it will also converge. Yeah, so it's just a trick. Like it's more rigorously should be called decoherence. So we use this trick, like choosing uniformly from a time interval to prepare a decoherent mixing state. Yeah, and it will converge. If it's always like just simulating Schrodinger equation, it's always a pure state, and just rotating. The phase is just rotating, and it will never converge. Right.
Can you clarify more about what do you mean measurement to become a state? Do you measure each position, or you randomly choose position and see where is the probability?
Okay. Yeah, it's like you have a state. The time is randomly chosen, but if you measure the position, it's just measuring the position, right? You do like in the quantum simulation case, you will discretize the space to simulate, and you just like each space, and you just do projections to get the probability on the like the discretized sites. And when you're doing this measuring, there is no like randomness. The randomness is that you choose the evolution time t randomly. Like you start from zero and you run a time t. This t is random, but if you just like random sample a t, right? You know this t now, and you do the measurement. The measurement is fixed. You just do projections of the states.
I see. So when you mean when you mention measuring the position, mean you measure all the position and calculate each position's probability and collect all the information to become a state, and you say the measuring time is random.
No, you don't need to do this. You you need to use this. What you said is actually how we analyze the result, but it's not how you do in the experiments, in the really optimization process. You just like do measuring, and the measuring result will just give you one result, like the point the particle is on the side, which will not give you the probability. It's just give you like the position, a fixed position. That's all, right? Not a fixed, just randomly give you a position, and you just use this position. And if you want to analyze it, you will calculate the probability of this position. But if you are just doing measuring in the process, it just gives you one position, one like.
I see. It's kind of
one
collects.
point.
Okay. It collects.
Yeah. Just right. It will just give you that point. And if you want to analyze it, okay, you need to analyze the probability of getting this position, right? But if you are just doing optimization, you measure it and it will give you a position. It will give you a point. That's all.
I see. And in your talk, you basically mentioned two examples. And for the second example, you mentioned a double whale. And
yeah.
And how's the? I think the whale already give you the potential of evolution direction, right? So why you need to analyze? Okay.
No, because in this SV region, this well is isotropic, which means in this SV region, I designed to not reveal the direction of V. So in this SV region, any point you ask, right, the function value of the points in this SV region depends only on the R, which is the distance from the point to the original point, which does not depend on the theta, the angle. It only depends on the distance between itself and the original point. So this is isotropic. It will not tell you any information about the direction. Yeah.
Sorry, I kind of confused. I thought your potential is the right one, the right figure, and the left figure. Are you try to make some analysis of the right potential? You are
okay.
To a simulation.
Yeah. The right figure here is illustration of this left one. The left one is actually an abstract one, which is true for high dimensional cases. And the right one is just like for two-dimensional cases, what will it look like? Okay. And actually,
Yeah, go ahead. Sorry.
Yeah, and inside this SV, actually, you can think like a slides here, a slides in this direction, right? And inside this SV, the function value is irrelevant to the direction.
Okay.
And as long as you're in it, yeah, your points are like randomly chosen with respect to V.
Okay.
So.
And so when you put into the quantum work, do you need to do some mapping, or you just put the potential directly? How do you put into the quantum work? You put it like the left equation.
Like I said here, if we need to start from a local ground state, so you need to prepare. You actually know one. In this problem, you know one minimum, the original point, and you want to find another. So if you know one, you can prepare a local state here, right? If you already know one, you can use like standard quantum techniques to prepare a state here. And then you initiate the.
You prepare in one well and they evolve into another one.
Yeah. That's how we do this. And for state preparation, we have like appendixes in the paper. to discuss this. Yeah. About quantum simulation and initial state preparation, we all discussed this in the paper. And here we mainly focus on the dynamics, which is the quantum tunneling evolution and the time. So if you want to find more about the query complexity and the initial state preparation, which is actually mainly done by previous works, right? You can find in the paper and the corresponding references.
Okay, thank you. Sorry, my final question is your first example, and how do you map it into quantum work? Do you mean it's the tensor case example? So what?
You mean here? Like I'm not mapping it to quantum walk. It's like it's similar to quantum walk, I should say, like this way, right? And here you also need to start from one minimum. And actually it's proved that finding one minimum is easy. And then you can prepare a local ground state here, right? And you evolve this local ground state, it will lead you to other minima. Like in this graph, this is like 3-dimensional case, right? It's just a landscape on the ball. And for the red points, they are local minimum, right? And
Yes.
Yeah, you go from this A1 to minus A3 or plus A2. Yeah, they are just local minimum.
So it's an example of multiple minimum, and you can do it in quantum work. Okay.
Yeah, actually in the subspace, in the linear subspace, and yeah, you can have such, it's not a rigorous map, it's just similar. You can think the local ground state as the state corresponding to a vertex, right? And you go between different vertexes, right? But it's not a rigorous map. Yeah, it's just similar.
I see.
Like
okay.
you go between wells, like you in graph, you go between vertexes. Yeah.
Okay. Thank you very much. Thank you for your nice talk.
Thank you. Thank you for your question.
Hi, and could you go back to the page that you talk about the advantage of the quantum tunneling algorithm? There's a page.
Later, this one?
Yeah. Later. You did 3 points.
Okay.
Next page.
Okay.
You mentioned there the width and the sharpness, and also the zero order distribution, and the other one.
Oh, you mean this one? Mean message. Okay.
Yeah. Okay. So could you explain more about the second and the third?
Okay.
Yeah.
Yeah, the second zero order property is like the distribution of wells. You can see this. You're calculating the, how to say, the spectrum gap of this interaction matrix. So when you're calculating the, like, you first you calculate the, how to say, the eigenvalues of this matrix, right? You want to diagnose this matrix and find its lowest and highest, lowest and the second lowest, like eigenvalues. And if this matrix is full, which means it's more symmetric, because every two well have some kind of tunneling strength, right? If this is full, and yeah, by linear algebra, you will find the gap is smaller.
Okay.
It's yeah. It's more symmetric. The gap is smaller, and if it's just a line, which means all this except the first the diagonal elements and the first diagonal elements, all other elements are zero. It's just a line, right? It's a line. And for a line, the spectrum gap is larger than the most symmetric case. So yeah, you will find that the distribution of wells, a line and most symmetric case will change the polynomial coefficients. Maybe I can't remember the detailed like which polynomial it is, but I can give you an example. Like for the most symmetric case, it's just n, and for this line, it's like n squared, something like this. Yeah.
So here you zero order means that the energy gap between the lowest quantity and the first excited state.
The order is just the landscape. The zero order means the distribution of wells. Like how to say, the minimum, the function value is 0, right? We say the distribution of points whose function is 0. So this is the order. It's just a function value property, or I should say, yeah. Sorry for the confusion. Yeah.
Okay.
Like the function value, yeah.
Okay, so this point you want to say that the energy gap will affect your algorithm performance. So if the energy gap is larger, and your algorithm will perform better.
Yeah.
Yeah. Okay.
Oh wait, is larger. Yeah, the time is smaller. Right. It's inverse gap, right? So the gap is larger. The larger the gap is, the better the algorithm is, right?
Okay. And what about the third part?
Third, yeah. The third point, like I said, the differential property. First, I should explain the differential property of this landscape. Is about the flatness. So you can think that at this local minima, I can take second derivatives, right? Or for high dimensional case, there is a Hessian. And the sum of the trace of this Hessian, like characterize the flatness. If the trace of this Hessian is large, which means this minima is very sharp. And if the trace is small, which means the minima is very flat. Right. And okay, the flatness, let me think. Yeah, the flatness will affect the shape of the state or distribution the algorithm will converge to. Okay, so this is also important. For classical case, it's simpler. For classical case, it will converge to a Gibbs state, which is e minus e to the minus like function value over s. So it's like the in thermodynamics, the Boltzmann distribution. Okay, so it's like for quadratic function, it's just a Gaussian distribution. And the flatness, if it's more flat, the Gaussian distribution will be like heavy tail, not heavy tail. Like it will have a longer tail, right? Its variance will be larger. So it's less accurate, right? And we find the flatness have different effects on the accuracies of quantum and classical algorithms. It's like on flatter minima, the quantum algorithm is more likely or is easier to get high accuracy. Like if the minima is very flat, the h can be larger to reach the same accuracy as the classical one. Or the s should be smaller to reach the same accuracy as the quantum one. And you say if s, we make the accuracy the same, right? Which means s is smaller, and the time needed for classical, if S is small, will be larger. So yeah, first, we compare these two algorithms based on the protocol that we make the accuracy the same. And second, the accuracy is affected by the flatness. And third, like for flat minima, the quantum ones are easier to get high accuracy. So this is how the flatness will affect the converge time. Like, yeah, you have 3 points.
So, so does this do these 3 points also apply to the quantum annealing?
Yeah, we think so. But yeah, this will be more complicated too. Yeah.
Okay.
But yeah, it will be inherent from here.
But before you implement the quantum annealing, did you have any advice how to see its flatness or the distribution of
see flatness? Okay, so
like if there's
this,
any guide
yeah,
to see this part.
Yeah. Actually, I think your question is a little not. I should say we abstract these properties to analyze, but in really applications, you cannot know the flatness, right?
Yeah,
or
yeah.
you cannot know some previous. I just say like if your landscape want to optimize, just like have very flat, then a flat minima, or you have some previous like knowledge or some kind of implicit knowledge that you know, oh, this landscape will have many flat minima, and okay, in this case, I can tell you that maybe you use quantum algorithm will be better.
Okay, I see.
So it's just like this case, yeah.
Okay, I see. Thank you.
Yeah.
Okay, is there any further questions? Okay. If there is no further question, let's thank Yizhou again.
Okay, thank you very much.
Thank you. Thank you for today's nice talk.
Yeah, thank you.
Thank you.